Today we start working with the volume of a region that, instead of being rotated around an axis, it's rotated around a line. All right? So let's take a look at an example here to get us rolling. Let's find the volume of the region that is bounded by x squared equals y minus 2 2y minus x minus 2 equals 0. X equals 0, x equals 1. But here's the kicker. This is what's a little bit different. It is rotated around the line y equals 3. Okay, which changes things a little bit. So it's critical that we understand our picture and have a good idea of what's going on here. So first things first, these equations up here, let's go ahead and solve them for y. So I would add 2 to both sides here. So y equals x squared plus 2. Simple parabola, moved up 2 units. On this one, I think I can do this all in one step. I think you probably could too. Add x, add 2, so that I have 2y equals x plus 2. And I would divide both sides by 2. So y equals 1/2 x plus 1. So we need to get these onto a graph, and I don't have room on this page to do that, at least not the right way. So x squared plus 2 and 1/2 x plus 1. I need to get those up on a graph. Make sure you leave some room on your graph to make markings and whatever. All right, x squared plus 2 is a simple parabola that has been moved up 2 units. So its vertex is right there on the x-axis at 2. I know that if I were to put in an x-coordinate of 2, it'd be up here at 4. Same thing for negative 2, be up here at 4. So I've got something like this. Graphing the situation is very important. Now, the other function, 1/2 x plus 1, is just a simple linear that goes through 1. So its y-intercept is 1, and I go up 1 over 2. I could come down 1 over 2. And I get, there's my 1/2 x plus 1. Now, we're also told that we're bounded by the lines x equals 0 and x equals 1. Now, I made a little goof and drew this thing a little too small. I apologize. But here's 0 and here's 1. So I have this little borderline right there, and right there. And the region I'm looking at, I'm going to color in this kind of pinkish purplish color. There's my region. And it's important that you know what the region is. So this region is rotated around the line y equals 3. So I have I'm just going to put a dashed line right here at y equals 3. And that's going to be the center. Okay, there is going to be a hole. Good job. Some of you are seeing that already. I'm going to take this region right here, and I'm going to rotate it. I'm going to try to get even another color here. Maybe I'll use green. And I'm going to rotate that thing up. Now let's see, I'm 2 units away there, so I'd be 2 units away there. So that deal would be rotated up around, and it would have an inner part that is also rotated around. And so there's going to be a hole. We have to think washer method. And if you remember, the washer method means I have to know the outer radius. Let's just write this down because this is going to give us our framework. It's the outer radius squared minus the inner radius squared. And of course it's the integral of that, and of course it's times pi. That's going to give us our roadmap for doing this problem. So if we look at that region, okay, and I think what I'm going to do is draw it a little bit bigger. You don't need to redraw it. But just for the sake of explanation, I'm going to make my units much bigger here. We've got this little, thing from 0 to 1. We've got a parabola, and then we've got this linear, all right, doing its business. And so this region right here in red is what's being rotated up around the line y equals 3. So we need to think of what the outer radius of this little mess is, of this little figure, this three-dimensional figure. So the outer radius, isn't it this? Isn't that the outer radius? Right? The outer radius, okay, because this is my center. Remember, we're rotating this thing around the line y equals 3. So my outer radius is the distance from 3 down to that function. Now, how could I find out what that distance is? If I happen to know a point, well, wouldn't I have to take 3 and subtract this distance? If I wanted to get the outer radius, which is this, okay, this right here is my outer radius. If I want to get that outer radius, all right, obviously the whole distance from here to here is 3. This is 3. Okay? So if I only want this, then I have to take 3 and subtract this blue.
So are we subtracting the integral of the...
So we are subtracting that bottom function. What was the bottom function? 1/2 x plus 1. Put it in parentheses. You have to subtract because that distance is changing depending upon the function value. This right here is your outer radius. Okay, 3 minus that bottom function, the 1/2 x. Here's 1/2 x plus 1. That's the outer radius. What do you think the inner radius is going to be? If I want to find the inner radius, then don't I have to take 3 and subtract this, the pink? So you're going to have to subtract the other function, the x squared plus 2 function. Okay, now those are kind of ugly right now, but we can clean them up a little bit. So I can take this one and make it 3 minus 1/2 x minus 1. So it's just 2 minus 1/2 x. And there is my outer radius. I'm going to put OR. And then I can take this other one and I can distribute, and I have 3 minus x squared minus 2. So that is 1 minus x squared, and that is my inner radius, IR. All right? And now, everything from that point on is just like what we've been doing. I would set up an integral. It's only going to go from 0 to 1 of that outer radius, which we said was 2 minus 1/2 x. 2 minus 1/2 x, quantity squared. We'll still have our pi out here because we're still slicing off cylinders, little flat cylinders. And I'm going to subtract the inner radius squared, which is 1 minus x squared. 1 minus x squared squared dx. So what I would do is, let's go ahead and you'd have to do some FOIL, do some simplifying before we ever start working with an antiderivative. So if I do FOIL here, I'm going to have 4, and I'm going to have, you know, when I do 1/2 x times 2, don't I get 1? So you're going to have minus 1x minus 1x. Yeah, you have to be careful when you're doing this FOIL. I'm probably being a little too risky here doing it in my head. Okay, 2 times 2 is 4. When I do 2 times 1/2, I get negative 1x. And I get the same thing in the middle. So your middle term is going to be minus 2x plus 1/4 x squared. And then when I FOIL this one, I have 1 minus x squared times 1 minus x squared, which would be 1 minus 2x squared plus x to the 4th. But I'm subtracting that whole mess. So I need to take a negative through. Minus 1 plus 2x squared minus x to the 4th. Hallelujah, we finally get to our dx at the end. So, we can simplify a little bit now. I now have the integral from 0 to 1 of 4 minus 1 is 3. I only have 1x to the 4th, so I'll just go ahead and write minus x to the 4th. but I have a 1/4 plus a 2. So that's like 2 1/4, which is 9/4 plus 9/4 x squared. And then I've got this little minus 2x tacked on the end, dx. Okay? And I need my pi out in front. So from there, it's a pretty straightforward polynomial. Let's just kind of go ahead and get to that antiderivative. This would be 3x. Of course, this whole thing is going to be times pi. 3x minus x to the 5th over 5 plus 9/4 times x cubed over 3 minus 2x squared over 2. All right, and that whole thing would be evaluated from 0 to 1. All right, so once you get that far, you should be pretty happy. And I could maybe do a little bit of factoring here. Of course, that becomes a 1. Here that becomes 3/4. So I would have pi times 3x minus x to the 5th over 5 plus 3/4 x cubed minus x squared evaluated from 0 to 1. All right, and then you would evaluate your integral. Obviously, it looks to me like the 0 part would be 0. All right, and you just finish it from there. Okay, and we are going to stop there for today.